Structural engineering isn't just about designing and building skyscrapers. It's a field of engineering that applies to a wide range of structures, big and small. In this video, we're going to explore the practical applications of structural engineering. By the end of this video, you'll be able to use some fundamental structural engineering principles to analyze everyday objects and even build a simple structure yourself. So let's get started. The first principle of structural engineering is understanding loads and forces. Loads are the forces that act on a structure, such as the weight of a building or the force of wind pushing against it. To be stable, a structure must be designed to support these loads. And it's important to understand how these loads are distributed throughout the structure. Imagine trying to hang a picture frame on a wall. You wouldn't want it to fall down, so you'd place a nail at an appropriate location on the wall to support the weight of the frame. In doing so, you've applied your knowledge of basic physics and structural stability. Similarly, when using a ladder, you would place it at an angle that ensures it won't slip and fall over. This is because you understand the concept of center of gravity and balance. Loads can be categorized into various types, including dead loads, which are the weights of the structure itself, and live loads, which are the weights of people or objects that may be placed on or moved around on the structure. Understanding how these loads are distributed and balanced is crucial in structural engineering. For instance, engineers designing a bridge must consider the weight of the bridge itself, as well as the live loads of the vehicles that will be crossing it. They also need to consider the forces of tension, compression, and shear that will be acting on the bridge. Tension is a force that pulls things apart, like the cables of a suspension bridge. Compression is a force that pushes things together, like the columns of a building. Shear is a force that acts parallel to a surface, like the force that holds together the layers of a sandwich. These forces can be difficult to visualize, but they're all around us. When you hang a picture frame on the wall, for example, the weight of the frame is supported by the nail, which experiences compressive forces. The wire used to hang the frame is in tension. And if you look closely at the frame itself, you can see that it's slightly twisted due to the shear forces acting on it. The second principle of structural engineering is understanding materials and their properties. Different materials respond differently to stress and strain. Stress is the force applied to a material, and strain is the resulting deformation of that material. Some materials, like concrete, are good in compression, but weak in tension. Others, like steel, are strong in both. By understanding these properties, engineers can choose the right materials for specific applications. For instance, concrete is often used for building foundations because it's strong in compression, meaning it can handle the heavy loads that a building places on its base. Steel is frequently used in construction because it's strong in both tension and compression. It's commonly used for bridges and buildings, as well as for reinforcing concrete, which, as mentioned before, is weak in tension. In fact, one of the earliest practical applications of structural engineering was in the construction of the Eiffel Tower. The tower was designed to withstand the compressive strength of concrete, but it was also necessary to reinforce the concrete with steel bars to resist the tensile and shear forces that would be acting on the structure. In addition to the type of material, its strength and stiffness also play a crucial role. Stiffness refers to the material's resistance to deformation under load. For example, when choosing wood for furniture, you might opt for a harder, stiffer wood like oak rather than a softer, more flexible wood like pine. This is because you want your chair to maintain its shape and not bend or sag over time under the weight of your body. Similarly, when building a bridge, engineers will consider the stiffness of the materials they're using to ensure that the bridge deck doesn't deflect too much under the weight of vehicles. A stiffer material like steel will be less likely to deform than a more flexible material like wood. In the next part of the video, we'll put these principles into practice by analyzing some everyday objects. We'll look at how engineers apply the principles of statics and material science to design everything from furniture to bridges. Before we move on, don't forget to hit that like button and subscribe for more engineering fun. Now let's continue. The third principle of structural engineering is understanding engineering principles in everyday objects. Almost everything we use every day has some sort of structural element. A chair, for example, has a seat and backrest, which are supported by four legs. The legs are like little columns holding up the rest of the chair. When you sit down, your weight pushes down on the seat. This force is then transferred through the chair's frame and legs to the ground. A table is another common piece of furniture that uses basic structural engineering principles. The tabletop is supported by legs or sometimes by a central pedestal. The legs provide stability and support, allowing us to place objects on the table without it tipping over. Bridges are impressive structures that allow us to cross over rivers and other obstacles. They typically consist of a deck supported by girders, which in turn are supported by piers or abutments. The deck is where vehicles and pedestrians walk or drive. The girders are horizontal structural members that span the distance between the piers or abutments, distributing the load across the structure. There are many different types of bridges, each using different structural principles and materials. But they all have one thing in common: they must be able to withstand the weight of what they're designed to carry, whether that's cars, trains, or pedestrians. And finally, buildings are probably the most complex structures we interact with daily. They're typically made up of walls, floors, and a roof, which are supported by beams, columns, and foundations. Walls provide stability and enclose the space, while floors and roofs provide surfaces for people to walk on. Beams are horizontal structural members that span the distance between two supports, such as the floor joists that support a wooden floor. Columns are vertical structural members that support the weight of the structure above them, such as the posts that support a porch roof. Foundations are the structural element that transfers the weight of the building to the ground. All these everyday objects are designed and built using basic structural engineering principles, including those of statics and material science. Statics is the study of structures at rest and how they support loads. Material science is the study of the properties and behavior of different materials and how they react to stress and strain. By understanding these principles, we can create structures that are not only functional, but also safe and efficient. Now let me quickly show you an example of putting these principles into practice. Let's build a simple structure like a mini bridge. We'll use basic materials like popsicle sticks and glue to simulate the behavior of real structural elements. You can do this along with me. Take two popsicle sticks and arrange them in a V shape. This is a basic structure of a truss, which is a framework made of connected structural elements that is used to span large distances. Trusses are efficient because they can distribute loads over a large area, making them ideal for bridges, roofs, and large structures like the Eiffel Tower. Now let's add some weight to our structure, simulating the load a bridge would experience from vehicles. As you add weight, you'll notice that the structure begins to bend. This is because the bottom stick is in compression and the top stick is in tension. To make our structure more stable, we can add more sticks to form a triangle. Triangles are the most efficient shape for distributing loads because they are rigid and cannot be deformed without breaking. Once you've added enough sticks to form a triangle, you'll notice that the structure is much more stable and can support a heavier load. This is because the sticks are now working together as a unit to distribute the load across the entire structure. Now let's remove some of the sticks and make the structure smaller. You'll notice that it's less stable and can't support as much weight. This is because there's less material to distribute the load and the individual sticks are weaker than the assembled structure. This is an example of the material's strength and stiffness playing a role in the structural integrity of a system, and that's it. We've built a simple structure and learned how to analyze it using basic structural engineering principles. Remember, structural engineering is all around us, even in everyday objects. By understanding the fundamentals of statics, material science, and structural analysis, you can appreciate the complexity and ingenuity that goes into designing and building structures that we use every day.